Hello everyone. Wanted to first tell you that I hope that everything is going well back at University Academy, and wanted to let you know that we are today going to talk about Hamiltonian paths. These are a special kind of thing that we do with vertex edge graphs. Thus far, when we talk about vertex edge graphs, you have seen some of the big ones. You've seen some work with trees. You saw some work with chromatic numbers. You have spent some time talking about some directed vertex edge graphs. Today we're going to talk about these Hamilton paths, and then we're also going to talk about Hamilton circuits. Let's think about this first, and let's actually first define what this means. Okay? So the story starts here with a guy named W.R. Hamilton, and Hamilton was a mathematician who invented this game called the Icosian calculus, where he had some icosahedron, which you know is a 20-sided polyhedron, and he had this game where he would challenge people to try and figure out a way that you could connect all of the vertices of this icosahedron and get back to where you started. It was kind of this interesting game, and as math folks do oftentimes, they try and optimize it, and they try and figure out some sort of unifying explanation for how you can solve a problem. Well, Hamilton actually kind of just stopped with that, but there are some other mathematicians who really got into trying to find these what we now call Hamilton paths and Hamilton circuits, and that's really where our terminology comes from today. So let's talk about Hamilton path. Okay? So a Hamilton path is a path through a vertex edge graph where all of the vertices are touched once. Okay? So a path through. This would be a good thing for you to write in your notes. Now, one of the things that's interesting here is that we're just saying that all the vertices are touched once. That means that you start at a point and that you finish after you have touched all of them. Well, if we juxtapose that Hamilton path with what we call a Hamilton circuit, instead of having that series of vertices, that path stops somewhere. A Hamilton circuit is one in which the path connects to the starting point. I'll give you a quick couple of examples here. Now, one of the things that I'll tell you before we get into actual pictures that go with these examples is that we denote these Hamilton paths and Hamilton circuits usually by a discussion of the vertices that it touches in order. Right? So, for instance, if I had just a basic 4-vertex oriented graph, I might say, hey, there's a Hamilton path that travels the route A, B, C, D. Now, you'll notice that it touches all 4 of those, and without seeing the graph, we're just going to assume it goes in this order. Now, Hamilton circuit, we would write in a similar manner, except we know that it's got to go back to its original spot. So, oftentimes we can take a Hamilton path and then just add one thing to get it to be a circuit. The other thing that I want to talk about with a Hamilton path before we look at these examples is that you have to understand that there might be multiple Hamilton paths in any graph. There's a reality that there might be no Hamilton paths in a graph as well. So let's take a look at this example. This is just a very, very basic vertex edge graph. There's no attributes or anything that are assigned to any of the edges or any of the vertices. And a lot of times when I'm searching for Hamilton paths, I like to use a highlighter. So that's what I'm going to do right now. Well, let's try and find one such Hamilton path. Okay. again, the idea is that I touch each vertex once. Now, I will end up, by virtue of the development of a Hamilton path, not going through all of the edges, and also not going through any of the edges twice. Not going through twice is not for any reason other than the fact that then we would end up revisiting more vertices than we want. So let's just do an easy one here, a simple one. I'm going to start at A, go to B, to F, to E, to H, to G, to D, to C. So that would be a Hamilton path. And I could explain that Hamilton path by saying I went from A to B to F to E to H to G to D and C. Now, it's important to understand that I don't have to go that route. Let's go through and let's take a look at a different one. And this time let's talk about the possibility of actually getting to a circuit. Let's say I'm going to go through, and I'm going to use pink this time. I go A to C to D to G to H to E to F to B to A. Now, it seems like that is the exact same route that I did before. But because I'm going in a different order and because I'm going back to that original spot, it's not. So A to C to D to G, H, E, F, B, A. And that's really kind of a sticky point when we start thinking about these things. It depends on which way we go. Now, one of the other fascinating parts about a circuit is that I write this circuit out based on the fact that I started at point A. Really, with a circuit, I could start pretty much anywhere. So I could have said, well, I'm going to start here at D, and my circuit might be D, G, H, E, F, B, A, C, D, and then back to G. So there's multiple ways that we could go through any circuit. Now, there are two ways really for us to try and find a circuit, and they're called the brute force method and the nearest neighbor method. They are actually very, very closely linked. Brute force means that I'm going to plot out any and every possible way for me to go through a graph, and I'm going to see which ones work and which ones don't. And knowing what we know about the fundamental counting principle, if I have 1, 2, 3, 4, 5, 6, 7, 8 different vertices, that's going to be a very sizable number of different options. In fact, using what we know from fundamental counting principle, we would actually end up seeing that the number of possibilities would be just 8 factorial, which at the end of the day is 40,320 different options. Now, I don't know about you, but I don't really want to go through and have to do each of those. So typically what we do is we use what we call the nearest neighbor method. And the nearest neighbor method is much like what I just did, and I just choose a spot. Let's start with E this time. And now I'm going to go to the nearest neighbor. And I'm going to choose the direction that I want to go. Let's see here. Let's go E to A to C. And because I've gone this route, I have to kind of keep going with the same direction. And then to D, to G. Really don't have any other options here. To H, started at E. So I'm going to just go up to F, and then to B. Now, the interesting thing is that I actually, at this point, cannot go and make a circuit. Right? So if I'm looking for Hamilton paths, this is a valid path. If I'm looking for Hamilton circuits, it's not. And so the premise here is that I would go through and I would just find all of these different ideas. Now, one of the fascinating things that we can add to a vertex edge graph and see really come to fruition when we start talking about Hamilton paths is that, well, we might give some attributes to these vertices and, more importantly, some attributes to the edges. So, for instance, let's take a look at this option, and let's say that this is a connection between cities. And I'm actually going to go ahead and say that these all connect. Not always the case, but it is in this one. So I'm going to add some attributes. I'm going to say that if I'm going to take the road between Rock Ridge and Blueville, well, that, let's say, is 10 miles long. Okay? And if I'm going to take the road that goes from Rock Ridge to Pulaski, well, that might be a road that is 8 miles long. From Blueville to Mill City, I may say that that's 12 miles long. From Blueville to Pulaski, I may say that this is 6 miles long. Mill City to Pulaski, I'm going to say that's 3 miles long. And then Rock Ridge to Mill City, that's a long one, we're going to say that's 20 miles long. So that means that if I'm going to go through and I want to take a Hamilton path, as I choose this, I'm actually going to be creating some sort of weighting for each of my paths. Right? So let's just go through one of these just to see what I mean. So let's go, let's use a different color that we can see a little bit better. So let's say I'm going to go Rock Ridge to Pulaski, to Mill City, and then back to Blueville, and from Blueville we go back to Rock Ridge. Right? So we're going to do a circuit. If I'm going to plot this out, I'm going to say that we started at Rock Ridge, then we went to Pulaski, then we went to Mill City, then we went to Blueville, back to Rock Ridge. Well, let's look at that. That path was 8 miles long. Pulaski to Mill City, we said that was 3 miles long. Mill City to Blueville was 12. And back to Rock Ridge was 10. Okay, so we would say that that Hamilton path, Hamilton circuit, has a weight of, let's see, this is 11 plus 12, which is 23 plus 10, so 33. Now, if I go through and I choose a different Hamilton path, I may end up with a very different weighting. Right? So, for the sake of argument, let's just go through and go around. Right? So, let's say I went to Rock Ridge, from Rock Ridge to Mill City, to Pulaski, to Blueville, and back. So, if I'm going to make that circuit, so Rock Ridge to Mill City, to Pulaski, to Blueville, and back. Well, now, this is 20. Mill City to Pulaski, 3. Pulaski to Blueville, we said was 6. And Blueville to Rock Ridge was 10. So, if I'm going to go in and add up all of these so I know what that whole weighting is, that's going to be 30 plus 9, so 39. If I'm trying to think of some sort of efficient way of doing it, this is going to end up being the more efficient path, circuit, in regards to this. If I'm trying to maximize for whatever reason, well, then this is going to be the more sought-after circuit. So I think about this sometimes as you're trying to waste time. If you were sent on some sort of mission where you were supposed to go from Rock Ridge to all these other cities, and you're borrowing a car that you really, really like, thinking about you as high school students, it might be that this is time that you get to spend with a friend that you're going to go on some sort of mission with, or a boyfriend or a girlfriend. So, of course, you're going to want to maximize time here. You're going to take the path that is the least efficient. Now, for us to go through and find what is going to be either the least or the most efficient method here is really still just going back to that idea of the nearest neighbor or that brute force. Nearest neighbor, well, what we would do is we would go through and see how many different paths we could do, and much like this, we would figure out how much each of them are. Brute force means that we actually go through and we calculate all of the different options, all of the different weights, and then from that list, once we have that comprehensive list, see which one is the best. Now, there are times with Hamilton paths that brute force is the only method, and there's no other way of getting around it. And in those cases, that's what you do. But in a lot of ways, there's times that the nearest neighbor method does work well. Tomorrow you're going to spend some time with something called the traveling salesman problem, and you'll see some of the applications of that brute force method. Okay, that is pretty much it as it comes to Hamilton paths and Hamilton circuits. Tomorrow we'll spend some more time with this. You have a in-class worksheet to work on, and then you have one for homework. Have a good rest of the day.